Section 12.4, we're going to take a look at similar triangles and other similar figures. So today's portion of it will be just the similar triangle part, and then we'll take a look at some other similar figure parts, I think. There's one part of this that talks about similar figures today, and then the rest of it similar triangles. So let's take a look at similar triangles. All right, so similar triangles. If two triangles are similar, do you notice, we talked about this when we did similarity before. There's that notation that looks like the tilde in between them, right? So triangle ABC, similar to triangle DEF. If and only if the angles paired up are congruent. So angle A is congruent to angle D, angle B to angle E, and angle C to angle F. And what happens between the two segment options is that you have proportional segments. So proportional side lengths. AB over DE is equal to AC over DF is equal to BC over EF. Proportional. So just a show of hands of curiosity, who has taken our math classes for proportional and statistical reasoning? Okay, so about 2/3 of you. Have seen proportions recently anyway. The rest of you have seen them before, obviously. But this is proportions from that section, which was chapter 7, actually. Okay, in other words, triangles are similar if and only if their corresponding angles are congruent and there is a common ratio called a scale factor among corresponding side lengths. That's what it means to be similar. There's a common ratio, they're proportional, and they've got congruent angles. You've got to have the congruent angles part for sure. Now, similar polygons have the same overarching feature. They have corresponding interior angles congruent and a common ratio called the scale factor among corresponding side lengths. Okay, so it's the same definition. You just have more angles to be dealing with or more corresponding side lengths to be dealing with. It's the only difference. And we talked about, when we talked about similar figures, that you see these all the time. Anytime something projects, like it's projecting on my overhead right now, that's a scale factor it's projecting by, right? Anytime you enlarge something on your computer screen, I don't know if you guys ever do that, but I do it inside of Microsoft Word. I'll enlarge or I'll shrink so I can see either the whole page or I can actually read it and I can see it up closer, right? It's doing it by a scale factor. It's doing this to your object, whatever you're working with. And I know you guys have done it for bulletin boards, right? If you've worked in the curriculum library, it's enlarging the letters with a scale factor. If you enlarge the K funky, it looks funky when you're done, right? You got to do it all entirely. All right, so there's there's three of them that we're going to look at today for triangles. There's the side-side-side similarity property. So if corresponding sides of two triangles are proportional, then the triangles are similar. So in other words, what it really takes to be similar is 3 of the common ratio parts, right, for the side lengths, and 3 congruent angles. It takes 6 facts, just like it did with showing that they were congruent. But these arguments, these propositions is what they're sometimes called, or theorems, or properties, depending on what your resource you're using, tell you that you don't really need all 6 to know for sure that it satisfies all 6. The first one says all you really need are the sides of 2 triangles that correspond to the sides of the other 2 triangles. All you need is really 2. 2 of the triangle sides, pairs of sides to actually work. So here's a diagram you can see here. This one actually shows some congruent angles in it, right? But you're taking a look at the 2 sides being proportional. So if you see the 6 here and the 12 here, what is the ratio with the 6 to 12? It's a 1-to-2 ratio, right? So if you looked at the side that's a 4 length, AB, it corresponds to which side? QP. And what would side QP's length be? 8. And what about the length of AC to PR? 14. They're all doubled, right? That's the ratio. Yes, Elsa?
So you said that you only need 2 sides in order to tell?
Yes.
Is that meaning one side from each triangle or 2?
It should be 2 pairs of sides. I don't think this picture is a very good one. It should have had another one marked on there for us to see that that worked. But that's what we would be looking for. Yes.
Okay.
Does in order to be proportional, you have to have two pairs to create the proportion.
Because then the third automatically.
Yeah, I think I need to change this to be in a different picture that I collected from online is my problem.
That's okay.
Yeah. Yeah, and you don't even need the angles marked at all, obviously, in order to satisfy the conditions on this particular one. Okay, let's take a look at the next one. Although the picture looks like it's cut off a little bit on yours, just to extend the end of your triangle on side DE. Looks like on the picture in my notes that this is cut off a little bit on your notes, is it? Yeah, a little bit. Just cut it off, attach it. You got it. Okay, so if two sides, and this really means two sides, not two pairs of sides, if two sides of a triangle are proportional and the included angles are congruent, then the triangles are similar. So, sorry, I was looking at my next one. Okay, so we have our two sides here. You've got the 6 and the 8, and you've got the 3 and the 4. Those are proportional, and the included angle is congruent, then the triangle is similar. Oh, I know what I said wrong over here. This is why this is making sense. This is all three pairs. If the corresponding sides of two triangles, this is, I think if we put the word all in here, that'll fix it. Put the word all here. All, if all corresponding sides are proportional, then the triangle is similar. That's the word I need in there.
So if there's only two?
If there's only two, you need the angle in between them, which is what the next one says. And that's why this is actually called side, side, side.
So if there's only two, we can't assume that the third one.
No, it wouldn't have to be. It wouldn't have to be, because they could have an angle difference. So like imagine, this is what I was struggling with before, imagine that you've got this 1:2 ratio here. So this is 2, and this is 4, and this is 3, and this is 6, but obviously the triangles that are created here are not proportional because the angle between them doesn't match. Does that make sense? So you either need the third side, which this one should have had marked appropriately. I'm going to change that picture for next time I teach it. Or you need the included angle to be matching. And this diagram has that. So you can see we've got the 1:2 ratio here. Here's the 4 and the 8 that correspond. And here's the 3 and the 6 that correspond, right? It is double. They're not always double, I promise. I should probably get an example when I fix the other one that's not double to prove my point. But they do have a congruent angle between them, or that matches here, right? That's what I wanted to do. This one and this one, they don't necessarily have to be right angles. This one just happens to be, but they do have to match each other. So far, the names of these two match the names of other congruency theorems that we had, right? Side, 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 and side, angle, side. They do. The third one is unique, though, because it's just angle, angle. And we even talked about with congruences that angle, 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 like knowing 3 angles, isn't enough, right? 3 angles isn't enough. Now, knowing 2 angles means you really know 3 angles, though, right? Yeah. Because if 2 angles are congruent, the third one has to be congruent. So you automatically get that. And if you have all the angles congruent, then you in fact do have similar triangles. So we have pairs of angles here. This one and this one, B and D are congruent. C and F are congruent. And they actually draw in more than you necessarily would need, but you can see a ratio here of some side lengths. And we could actually use what's on here to solve for X. For example, the 8 here corresponds to the 6 because it's between the corresponding angles that are marked congruent, right? So if you looked at the factor, the scale factor here, you could either say that to go from here to here is 6 compared to 8, or you could say to go from the right one to the left one is 8 compared to 6, depending on which direction you're going. And you could set up the ratio then that would make us be able, or let us, not make us, but let us be able to find the side X because it corresponds to the 5. Okay, so the way that you would do that, I haven't actually shown you how to do that on any of these. Let me actually clear some of this off. Let's say that we're actually, let's just go this direction from left to right because that's how we write. So this ratio goes from a side 6 in the left-hand triangle to a side 8 in the right-hand triangle. And on the left-hand triangle it is a 5 compared to on the right-hand triangle it is an X that are corresponding. Now we have fractions, we have proportions, however you want to think about this. We should be able to solve this for X. What's the first step in solving this for X?
5 times 8.
Okay, so do you know what you're doing, what it's called, Hannah?
It's cross multiplying.
Cross multiplying is what people sort of shorthand call it. So if we multiply across, like Hannah is suggesting, we can do like this. And we get 6 times x, which is 6x, and 5 times 8, which is 40. And then what will we do? Divide by 6. And if we leave it written as a fraction, because nobody said we couldn't on this, right? This would be 20/3. If you want it written as a mixed number, just for practice because it's so much fun, what's a mixed number here look like? 6 and 1/3. 2/3, sorry. 2/3 left. 6 and 2/3. If you write it as a decimal, it's a repeating decimal. Does anybody know what that decimal looks like? It's 6.6 repeating. Yeah. So any of those would be acceptable measurements for the length of x. We're not particular on which one. You do need the repeating bar if you're going to do the decimal on this one to indicate that it is repeating. So we're not rounding it off.
Does it matter which format I am using?
It doesn't matter to me unless the problem actually asks you to do something specific. Yeah. All right, and we will pick up next time with properties of proportions.